Hey there, chemists. In this lesson, we're going to start to look at the alcohol functional group and specifically focus on ways that we already know to make the alcohol. Also the ether, which we're going to sort of learn about at the same time. The first thing you see in your notes is just a graphic that shows you how you can make an alcohol from a variety of different functional groups that some we've seen a lot about and some we haven't. And also how you can turn alcohols into a variety of other functional groups. So you can think of that functional group as a very versatile one, because once you get there, you can get to almost any other functional group, at least in a step or two. Some terminology that you should be familiar with is if we say a primary alcohol versus a secondary versus a tertiary alcohol, that refers to the number of carbons attached to the alcohol carbon. So this ethanol is an example of a primary alcohol because there's exactly one carbon attached to the alcohol carbon. Isopropanol right next to it has 2 carbons attached to the alcohol carbon. T-butyl alcohol has 3 carbons attached to the alcohol carbon. So when we say primary, secondary, tertiary, that's what we're talking about. And it takes different types of reactions to make those types of alcohols. So let's just go through and remind ourselves of some of the reactions that we already know. And if you want to challenge yourself, hit pause right now and see how many of these you can fill in on your own and then come back and check. Okay, so the first one is an alkene reaction, the hydration of alkenes. That's just hydronium and an alkene. This gives you Markovnikov addition of H and OH, and I'll remind myself of that by writing Markovnikov right below it. This particular example would give me a racemic mixture. You get a mixture of stereoisomers when you do just hydrolysis of an alkene in this fashion. It's reversible, remember. You can do an elimination. That's an E1 in the opposite direction. We can control that with the Chatelier's principle. Right below it is actually the same transformation, but it's a little more stereoselective. This is oxymercuration. You also get Markovnikov addition of H and OH. Now, I can't tell in this example, but you do get anti-addition as well. So if we were using, let's say, a cyclic alkene in this example that was branched, for example, methyl cyclohexene, we would see addition across that alkene such that the H and the OH are in opposite directions. Actually, that example I wouldn't be able to tell either, but if I had a more substitute alkene, we'd be able to see that. Below that, we get the non-Markovnikov version. Hydroboration with borane followed by base and peroxide gives you the non-Markovnikov addition. So I would get a primary alcohol with this alkene. So non-Markovnikov. And this proceeds with syn addition. And that's, remember, because of the actual concerted step involving the addition of borane to the alkene. You get an H attached to a borane, and then those bonds form at the same time, so you get syn addition of what becomes an H and an OH. Dihydroxylation is how you add 2 alcohols to an alkene. So there's neither Markovnikov nor non-Markovnikov for this transformation, but there still is relative stereochemistry. This occurs with syn addition. I can't tell in this particular example, so I'm not showing it, but if it was cyclic, you would see 2 hydroxyls coming off of the same face of the cyclo whatever. And epoxidation is a way of making an ether. MCPBA is the per acid that works for this. This also has neither Markovnikov nor non-Markovnikov, but it's also a syn addition. So that's that first column. Let's pan over and do a few others. Now we're getting into our alkynes unit, our most recent unit prior to this one. And this is how we can make alcohols from the organometallic, the alkyne anion. Remember that sodamide, NaNH2, simply makes an anion off of a terminal alkyne. That can attack an aldehyde, which pushes the electrons of that carbonyl up, and then the H plus protonates that oxygen. So you get 2 new carbons attached to that terminal carbon, and then an OH one away from the alkyne. So that would give me my starting alkyne, 2 new carbons, and in this case, a secondary alcohol. what we're going to see later on in this unit, actually starting with the next lesson, is that there are many other organometallics that one can use to react with aldehydes to give you secondary alcohols. The anion of this alkyne is the first of a whole class of reagents called organometallics. Right below that, it's the same transformation, except we have a ketone instead of an aldehyde. You can picture just a little bit of the abbreviated mechanism in your head. You make the anion on that carbon, it attacks the ketone, the electrons go up, you protonate, you get something very similar to what we had up above. All the carbons of your alkyne are still there, but in this case, you will get a tertiary alcohol. And then there's one other to add to this list with the alkyne anion. Again, it's making the anion and attacking an epoxide. Epoxides are great little functional groups. You can make them quickly from alkenes, and they add at least 2 carbons. And then remember how this works. When you have, I'm actually going to draw this in actual ink. If you have an anion on this carbon, that acts as a nucleophile for the epoxide, and under anion conditions, let's say basic conditions, epoxides open at the less substituted side if it's not symmetrically substituted. So you'll attack that carbon, and then the 3-membered ring will open up. That gives me, in this case, the 4 carbons from the alkyne, and then I have 3 more carbons attached, 1, 2, and 3. And then we have this carbon-oxygen bond still there. That's on that carbon right there. I'm actually going to modify this epoxide just to show how this has a little bit of stereoselectivity to it. I'm going to change this so that that bond actually has some direction to it. And you'll see why. The point of that is that this doesn't have anything happening to it. So whatever the stereochemistry is for that bond, it's still there in the alcohol that you end up making. I'm just going to say makes an alcohol. I'm not going to write tertiary, primary, or secondary because it really depends on how substituted the epoxide is. Okay, and then the last one from sort of the old reactions that we've learned, this is an ether synthesis. It's one of the most useful ones. It's called the Williamson. It's really just an acid base followed by an SN2. Most common base we use is sodium hydride. That's just an H- anion coordinated to an Na+. This acts as a base. It takes the H away, so you temporarily form an alkoxide, meaning the anion of the alcohol, and then that sees, in this case, bromomethane, and it will do an SN2. So this has limitations such as I want to make sure my acceptor is very unhindered, things like methyl, primary, maybe secondary acceptors, all the things we know from the SN2 reaction many units ago. So the point of that was to give you a nice comprehensive summary of all the reactions you actually already have. They're just reactions of alkenes or reactions of alkynes or maybe SN2 steps, but they all have things in common like making alcohols and ethers. There's only one new thing today, and it's really not even that new. It's an application of some other stuff we've seen, and it's how we can open up epoxides. We actually saw that up above a moment ago with the alkyne anion, and I mentioned that it happens on the less substituted side when you're in base. You can turn that around if you make it acidic. So this first example is acidic conditions. And if I have an epoxide like this one, and I treat it with a source of H+ and an ethanol, you get the following. Opened epoxide. I'll get an ether on one side and an alcohol on the other. So how did we get that? Well, the first step is simply protonation of the oxygen. That gives me what we call an oxonium, just a positively charged oxygen. And that should look reminiscent of things like the bromonium ion or the mercurium ion that we saw in the alkene unit. And indeed it is. It's this positively charged 3-membered ring. So it has the potential to open up, and the side that's going to feel more like it's positively charged, this is the one that's going to carry the positive charge. So I have a very substituted side of this epoxide versus a much less substituted side. And it's the more substituted side that's going to feel like it has that positive charge. So when ethanol sees this molecule, it will attack the more substituted carbon. So you get an OH on the less substituted spot and a positively charged ether on the other. How do I get to that actual product? Well, we put an H plus on in the first step, so we're going to take an H plus off in the last step. That's a very common thing in acid catalyzed reactions. Anything that's remotely basic could do it. Even just another ethanol molecule could take that away. And that's how you get to your opened epoxide. So what's the difference between this and the one right next to it? Well, the one right next to it is under basic conditions. This is essentially the same kind of reaction, but this is basic. And the product here has it opening up at the other side. You'll actually get an OH that's tertiary and an ether on the primary carbon. So how did this happen? Well, under basic conditions, you attack the less substituted side. So that OET minus, that ethoxide, is going to attack the less substituted carbon, just like the alkyne anion did up here in this example. Basic conditions, negative charges, attack the less substituted side of epoxides. That'll give you an intermediate with an O negative on the more substituted side and an O ethyl right where we see it in the product. And then how do I get to my product? Well, I'm apparently in ethanol as a solvent or something, so I can use ethanol as a proton source and just protonate that oxygen anion. So to summarize, just those two reactions, and those are really the only new ones in acid epoxides open at the more substituted side. However, in base epoxides open at the less substituted side. And you know what you're in simply based on charge. Bases are anions. So when I say base, we're talking negative charges. Acids, we're talking positive charges. Okay, so that's a summary of all the reactions that you've seen so far, most of them, that make alcohols, and a couple that make ethers and epoxides, and just one main new one about opening epoxides.